All right, let's talk about one of the biggest, most beautiful, and honestly, most complicated puzzles in all of climate science. Clouds. I mean, they cover about 70% of our planet at any given time, but their exact role in our future has been incredibly difficult to figure out. So, what is it that makes them such a wild card?
Well, here's the thing. Clouds are kind of playing for both teams at once. Some of them act like a giant sunshade for the planet, reflecting sunlight back into space and cooling us down. But others act more like a blanket, trapping the Earth's heat and warming us up. And the exact balance between those two effects, that is one of the single biggest uncertainties we have in predicting just how warm our world is going to get.
You know, at the very heart of this mystery is a massive data problem. For decades, scientists have been trying to figure out how to classify and track these constantly shifting patterns all over the globe. How do you see the big picture without losing all the tiny, critical details? And this right here is the classic problem they were facing. If you look at cloud data day by day, it's just a chaotic mess. It's too much information, too much noise to make sense of. But if you try to simplify it by averaging everything out over a whole season, all the important patterns just blur together into this featureless fog. It's like trying to understand a whole forest by looking at either one single leaf or a super blurry photo taken from a satellite. Neither one really helps. So you see the problem, right? Scientists were completely stuck. They desperately needed a new way of looking at things, a method that could let them see both the fine, day-to-day details and the grand seasonal patterns all at the same time. They needed something that could finally bring the planet's cloud behavior into sharp focus. And that's where this breakthrough idea comes in. It's got a pretty cool name too. Regimes of regimes. This is a concept from a team of NASA-affiliated scientists that totally changes the game in how we look at clouds. Let's break down how they did it. Okay, so how on earth does this work? It's actually pretty clever. First, they take these daily satellite snapshots of different cloud types, which they call cloud regimes. Then, for every single spot on the globe, they group these daily snapshots into rolling 3-month windows. This basically creates a seasonal recipe. You know, the unique mix of cloud types that a region experienced over that time. And then, get this, they took 15 million of these seasonal recipes and fed them into a super powerful algorithm with one simple instruction: find the patterns. And what popped out the other side? Something they call regimes of regimes, or RORs for short. The algorithm found that you can boil down all the crazy, complex seasonal cloud patterns on Earth to just 8 distinct types. Think of them as the planet's 8 fundamental cloud personalities. This new method finally gives every region on Earth a clear seasonal cloud identity.
So, what are these 8 cloud personalities? Let's meet a few of the big ones, the key players that really shape our planet's climate.
First up, you've got OR1. Think of this one as the tropical rainmaker. It's defined by this powerful mix of deep, towering thunderstorm clouds and the high, wispy clouds they leave behind. You find this personality all over the tropics, driving huge weather events like the Indian monsoon and other major storm systems.
Then there's ROR2, which we can call the mid-latitude storm tracker. This is the personality you see over the world's huge oceans, a churning mixture of thick, low-lying stratus clouds and the big storm systems that march across the mid-latitudes. Now, this next one, pay close attention to this one. It's ROR5, the ocean's cooling puffs. This personality is made up of these vast fields of shallow, puffy cumulus clouds you see over subtropical oceans. The key thing about them is that they're super bright white and they cover these massive areas, which, as you'll see, gives them a really powerful effect on sunlight. And just to show you the full range, on the complete opposite end of the spectrum, you've got something like ROR8, the semi-clear skies. This is the personality that defines places like the Sahara Desert or the poles, where clouds are pretty rare and the air is generally dry. Okay, so we have these 8 cloud personalities. Cool, right? But why is this such a big deal? Well, it's because this new system lets us do something we've never been able to do accurately before: precisely measure how each one messes with Earth's thermostat. It all comes down to something called the cloud radiative effect, and it's pretty simple, really. Low, bright clouds, like our storm tracker ROR2 and those cooling puffs of ROR5, are fantastic at reflecting sunlight, so they have a strong cooling effect. High, thin clouds, like the ones in the tropical rainmaker ROR1, are better at trapping heat rising up from the Earth, which creates a warming effect. But here's the bottom line. When you add it all up, most of these cloud types actually have a net cooling effect on our planet. They help keep us from getting too hot. And we're not talking about a small effect here. It's massive. Take ROR2. that stormy ocean personality we talked about, it cools the planet by about -7 watts per square meter. Now, that might not sound like a lot, but the total cooling from all clouds combined is around -20. So just that one cloud type is doing more than a third of the heavy lifting. That's huge.
So we have this amazing new tool for understanding clouds. And this is where the story takes a pretty concerning turn. Because when the scientists used this new method to look back over the past 2 decades, they found something alarming.
It turns out one of these key cloud personalities isn't behaving like it used to. It's changing. Its footprint on our planet has been steadily shrinking over the last 20 years.
And here it is. This is the smoking gun from their research. The population of ROR5, remember that one? The ocean's cooling puffs, those bright, shallow clouds over the subtropics? It is in decline. It's becoming significantly less frequent.
I mean, the researchers themselves point this out directly in their paper. They say, and I'm quoting here, that this shallow convection type stands out, largely because of its declining population. Out of all 8 types, this was the trend that just jumped right off the page.
So let's just pause for a second and make sure this sinks in. A specific type of cloud, one that we know has a major cooling effect on the planet because it reflects sunlight back into space, is slowly disappearing. We are literally losing a piece of our planet's natural sunshade.
And so, this incredible new way of seeing our sky leaves us with a really unsettling question. We have this natural air conditioner for the planet, right? And what this research shows is that it's starting to break down. So the real question now is, as these crucial cooling clouds continue to vanish, how much faster is our planet going to warm up?